Hello, young scientists! Today we're diving into the fascinating world of electrochemistry. Have you ever wondered how batteries power your phone or how cars run on electricity? The answer lies in the intriguing relationship between chemical reactions and electrical energy. This is precisely what electrochemistry explores, the interconversion of chemical and electrical energy. Electrochemistry is not just a theoretical concept confined to textbooks, it's a fundamental process that powers our lives. From the batteries in our devices to the production of metals like aluminum, electrochemistry plays a vital role. Even the rusting of iron, a common phenomenon, is an electrochemical process. Understanding electrochemistry unlocks a world of knowledge about how energy works and how we can utilize it efficiently. So buckle up and get ready to explore the wonders of this electrifying field. As we delve deeper into the world of electrochemistry, we will uncover the principles behind these applications and many more. Get ready to be amazed by the power of electrochemistry. At the heart of electrochemistry lie electrochemical cells, ingenious devices that serve as the bridge between chemical and electrical energy. These cells are fundamental to many technologies we rely on daily, from the batteries in our smartphones to the large-scale energy storage systems that power entire cities. Understanding how they work can give us insights into the future of energy and technology. These cells are like tiny power plants, either generating electricity from chemical reactions or using electricity to initiate chemical transformations. They are the unsung heroes behind many modern conveniences, quietly converting energy forms to keep our devices running and our lives moving smoothly. There are two main types of electrochemical cells: galvanic cells and electrolytic cells. Each type operates on distinct principles and serves different purposes, yet both are crucial in various applications, from industrial processes to everyday gadgets. Galvanic cells, also known as voltaic cells, harness spontaneous chemical reactions to generate electrical energy. These cells are the backbone of many portable power sources, providing a steady flow of electricity whenever and wherever it's needed. Imagine a battery powering a flashlight. That's a prime example of a galvanic cell in action. The chemical energy stored within the battery is converted into electrical energy, which then powers the light, illuminating our path in the dark. Inside, chemical reactions release energy, causing electrons to flow, ultimately powering the light. This flow of electrons is what we recognize as electricity, a vital force that drives countless devices and systems in our world. On the other hand, electrolytic cells operate in reverse. Instead of generating electricity, they consume it to drive chemical reactions that wouldn't occur spontaneously. This reverse operation opens up a whole new realm of possibilities in chemical manufacturing and material processing. They utilize electrical energy to drive non-spontaneous chemical reactions. This process is essential in various industries, from producing metals like aluminum to purifying chemicals, and even in the field of electrolysis for water splitting. Think of electroplating, where a thin layer of metal, like gold or silver, is deposited onto another metal surface. This technique is widely used in jewelry making, electronics, and automotive industries to enhance appearance, prevent corrosion, and improve wear resistance. This process relies on an electrolytic cell using electricity to force the deposition of the desired metal. The precision and control offered by electrolytic cells make them indispensable in creating high-quality, durable products. Both galvanic and electrolytic cells consist of essential components: electrodes, electrolytes, and often a salt bridge. Each component plays a critical role in the cell's operation, ensuring the smooth flow of electrons and ions necessary for the chemical reactions to occur. Electrodes, typically made of metals or other conductive materials, serve as the sites where chemical reactions occur. They are the heart of the cell, where the magic of energy conversion happens, transforming chemical energy into electrical energy or vice versa. The electrolyte, a solution containing ions, facilitates the flow of charge within the cell. It acts as a medium that allows ions to move between the electrodes, completing the electrical circuit and enabling the cell to function effectively. The salt bridge, present in many galvanic cells, maintains electrical neutrality by allowing the movement of ions between the two half cells. This component is crucial in preventing the buildup of charge that would otherwise stop the cell from working. Understanding the differences and inner workings of galvanic and electrolytic cells is crucial to grasping the fundamental principles of electrochemistry. This knowledge not only helps us appreciate the technology we use daily, but also paves the way for innovations that could revolutionize how we generate, store, and use energy in the future. Now that we've explored electrochemical cells, let's dive deeper into the concept of electrode potentials. Electrode potentials are fundamental to understanding how electrochemical cells work. They help us predict the direction of electron flow and the feasibility of chemical reactions. By examining electrode potentials, we can gain insights into the behavior of different metals and their ions in solution. Imagine you have two different metals, like zinc and copper, each dipped in a solution containing their respective ions. These metals, when placed in their ionic solutions, exhibit unique behaviors. Zinc, for instance, tends to lose electrons more readily compared to copper. This difference in behavior is what we quantify using electrode potentials. Do you think they'll have the same tendency to lose or gain electrons? The answer is no. Each metal has a distinct tendency to either lose or gain electrons, which is influenced by its intrinsic properties and the nature of the solution it is in. This is where the concept of electrode potential becomes crucial. Electrode potential quantifies the tendency of a metal to lose or gain electrons when it's in contact with a solution of its ions. This measurement is essential for understanding the electrochemical behavior of metals. By measuring the electrode potential, we can determine how easily a metal can be oxidized or reduced. This tendency is measured in volts and is a crucial factor in determining the voltage and direction of current flow in an electrochemical cell. The greater the difference in electrode potentials between two metals, the higher the voltage of the cell. This voltage drives the flow of electrons from one metal to the other, creating an electric current. To standardize this measurement, we use the standard hydrogen electrode, or SHE, as a reference point. The SHE provides a consistent baseline for comparing the electrode potentials of different metals. It is a crucial tool in electrochemistry, allowing scientists to accurately measure and compare the tendencies of various metals to lose or gain electrons. The EEE is assigned a potential of 0 volts, and all other electrode potentials are measured relative to it. This standardization simplifies the comparison of different metals' electrode potentials. By using the SHE as a reference, we can easily determine whether a metal is more likely to be oxidized or reduced compared to hydrogen. This allows us to compare the relative tendencies of different metals to lose or gain electrons. Metals with higher electrode potentials are more likely to gain electrons and be reduced, while those with lower potentials are more likely to lose electrons and be oxidized. This information is vital for predicting the outcomes of electrochemical reactions. The Nernst equation, a fundamental equation in electrochemistry, comes into play when we deviate from standard conditions. It allows us to calculate the electrode potential under non-standard conditions, taking into account factors such as temperature, pressure, and the concentration of ions in solution. This equation allows us to calculate the cell potential under non-standard conditions, considering factors like temperature and the concentration of reactants and products. By using the Nernst equation, we can predict how changes in these conditions will affect the electrode potential, and consequently, the overall cell potential. Understanding electrode potentials is crucial for predicting the spontaneity of reactions, calculating cell potentials, and comprehending the driving force behind electrochemical processes. By mastering this concept, we can better understand the principles governing batteries, corrosion, and various industrial applications of electrochemistry. This knowledge is not only fundamental to chemistry, but also has practical implications in fields such as energy storage, materials science, and environmental science. Imagine using electricity to split water into hydrogen and oxygen gas. This process, known as electrolysis, is a fascinating demonstration of how electrical energy can be harnessed to drive chemical reactions that wouldn't occur naturally. By applying an electric current to water, we can break the bonds between hydrogen and oxygen atoms, resulting in the formation of gas bubbles at the electrodes. This is just one of the many incredible applications of electrochemistry. Another intriguing example is the electroplating process, where a thin layer of metal such as silver is deposited onto a surface. Imagine taking an ordinary spoon and transforming it into a shiny, silver-coated utensil. This is achieved by immersing the spoon in a plating bath and passing an electric current through the solution. The metal ions in the solution are attracted to the spoon, forming a smooth, even coating. This technique is widely used in various industries to enhance the appearance and durability of metal objects. These fascinating processes are made possible by electrolysis, a powerful application of electrochemistry. Electrolysis is not just limited to splitting water or electroplating. It has a wide range of applications in both scientific research and industrial processes. By understanding the principles of electrolysis, scientists and engineers can develop innovative solutions to complex problems, from energy storage to material synthesis. Electrolysis involves using electrical energy to drive non-spontaneous chemical reactions. In other words, it forces reactions to occur that wouldn't happen on their own. This is achieved by passing an electric current through an electrolyte solution, which contains ions that can move freely. The electric current causes these ions to migrate towards the electrodes, where they undergo chemical changes. This process can be used to produce a wide variety of substances, from pure metals to complex chemicals. In simpler terms, it's like forcing a reaction to occur that wouldn't happen naturally on its own. This ability to control chemical reactions with electricity opens up a world of possibilities. For example, electrolysis can be used to extract metals from their ores, produce chemicals like chlorine and sodium hydroxide, and even generate hydrogen fuel for clean energy applications. The versatility of electrolysis makes it an invaluable tool in both scientific research and industrial production. This is achieved by passing an electric current through an electrolyte, causing chemical changes at the electrodes. The electrolyte solution contains ions that are free to move, and when an electric current is applied, these ions migrate towards the electrodes. At the electrodes, the ions undergo chemical reactions, resulting in the deposition or liberation of substances. This process is governed by Faraday's laws of electrolysis, which provide a quantitative understanding of the relationship between the amount of electricity passed through the cell and the amount of substance deposited or liberated. Faraday's laws of electrolysis govern the quantitative aspects of this process. The first law states that the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the cell. This means that by controlling the amount of electric current, we can precisely control the amount of substance produced. The second law establishes a relationship between the amounts of different substances liberated by the same quantity of electricity and their equivalent weights. These laws are fundamental to understanding and optimizing electrolysis processes. The first law states that the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the cell. This principle is crucial for applications such as electroplating, where precise control over the thickness of the metal coating is required. By adjusting the electric current, we can achieve the desired coating thickness with high accuracy. This level of control is essential for producing high-quality, durable products in various industries. The second law establishes a relationship between the amounts of different substances liberated by the same quantity of electricity and their equivalent weights. This means that the amount of substance produced during electrolysis depends not only on the quantity of electricity, but also on the specific properties of the substance itself. Understanding this relationship allows scientists and engineers to predict and control the outcomes of electrolysis processes, making it possible to produce a wide range of materials with precision and efficiency. From extracting metals from their ores, such as aluminum and copper, to refining and purifying these metals for use in various applications, electrolysis plays a crucial role. The ability to extract and refine metals efficiently is essential for industries ranging from construction to electronics. Without electrolysis, many of the materials we rely on today would be much more difficult and expensive to produce. To producing chemicals like chlorine and sodium hydroxide, which are essential for a wide range of industrial processes. Chlorine is used in the production of plastics, disinfectants, and solvents, while sodium hydroxide is a key ingredient in the manufacture of paper, textiles, and detergents. The ability to produce these chemicals through electrolysis ensures a reliable and efficient supply for various industries. Electrolysis plays a vital role in various industrial processes. Its applications extend beyond metal extraction and chemical production to include water treatment, energy storage, and even the generation of hydrogen fuel. The versatility and efficiency of electrolysis make it an indispensable tool for modern industry, driving innovation and enabling the development of new technologies. It's a testament to the power of electrochemistry to drive chemical reactions and create valuable products. From everyday items like silverware to advanced materials and clean energy solutions, electrolysis has a profound impact on our lives. By harnessing the power of electricity, we can unlock new possibilities and continue to push the boundaries of what is possible in science and industry.